Good day. Today we are going to discuss about the midband analysis or small signal analysis. The purpose of small signal analysis is used to calculate the midband voltage gain or midband current gain or midband transconductance gain or midband transresistance gain. The following procedure is adopted to perform the small signal analysis. Step 1. Consider the effect of AC sources alone. So we have to consider the effect of AC sources only. Step 2. Null the effect of independent DC sources. Suppose the circuit has independent DC voltage source, then we have to short it. Suppose the circuit has independent DC current source, then we have to open it. We should not null the effect of dependent DC sources. Okay, please remember, we have to null the effect of independent DC sources only, not dependent DC sources. Next one, treat all coupling and bypass capacitors as short circuited. Then treat all parasitic capacitance as open circuited. The next step, draw the small signal equivalent circuit diagram. Normally, the small signal equivalent circuit diagram consists of small signal model of a device and its biasing elements. The last step is we have to calculate the small signal voltage in AV, which is the ratio of AC output voltage by AC input voltage, or current gain AA is the ratio of I0 by IS. Transconductance gain GM is the ratio of I0 by S, and transresistance gain RM is the ratio of V0 by IS. Now we are going to do the midband analysis or small signal analysis on common emitter amplifier. So common emitter amplifier circuit is given. We are going to do it. So let us follow the steps. So the step number 1 is consider the effect of AC sources only. So there is only one AC source. We have to consider this AC source. Okay. Then step number 2 is null the effect of independent DC sources. So there is only one DC sources here, VCC. We have to null the effect of independent DC sources. The given DC source is the voltage source, so we have to short it. We are going to short the DC sources. Then treat all coupling and bypass capacitors as short circuited. So we know that capacitive reactance XC for coupling and bypass capacitor 1 over 2 pi FC. The frequency of operation normally during midband analysis will be megahertz, and capacitance range will be microfarad. So mega and micro, megahertz and microfarad get cancelled. So what is the capacitive reactance we will get? We will get some fraction. So that values we can treat it as a shorted one. Okay. So what we are doing, because of the capacitive reactance of this coupling and bypass capacitor during midband, it offers closer to zero value as the resistance. Hence we are short circuiting the coupling and bypass capacitances. Then what about these parasitic capacitances? These two parasitic capacitances, C pi and C mu. These two capacitances are otherwise called internal capacitances. The typical value of this parasitic capacitance will be C mu and C pi will be in the order of picofarad or femtofarad. So let us assume it is in the order of femtofarad, 10 to the power of minus 15. So what is the capacitive reactance offered by C pi or C mu? 1 over, once again the same formula, 1 over 2 pi FC. F will be megahertz, 10 to the power of 6. C will be 10 to the power of 15. Then what will happen? 10 to the power of this 15 minus 15, 6, 10 to the power of 6. They get cancelled, 2 to the power of 9 divided by 2 pi. So what happens? This will be very large. 10 to the power of 9 will be giga ohms range. So it offers a very high impedance or very high reactances. Hence we can treat these two capacitances C mu C pi as a open circuit one. That is given in the point number 4. Now what we have to do is we have to draw the small signal equivalent circuit diagram. The small signal equivalent circuit diagram consists of small signal model of a device and its biasing element. This device, this is your BJT device. For this device, small signal model of a device is, already we know that GM into V pi R naught R pi. Here output is, we can say V naught. This point potential is V pi. This is a small signal model of a device. So now what we have to do is, the now active device replaced by the small signal model. Okay. So what we have to do is, let me redraw this circuit diagram by considering the step number 1, 2, 3 and 4. Okay. Vs, Rs, R1 parallel to R2, Re shorted, then Rc, this point is grounded, RL, V naught. For this device, this is the model. Okay. Now what we are going to do is, we are going to draw the small signal equivalent circuit diagram. The small signal equivalent circuit diagram consists of small signal model of a device and its biasing element. So first let us draw the small signal model of a device. GM V pi R naught R pi base collector and emitter node. Okay. So let us go and stand physically at base node. What we can see, with respect to this node, R1 and R2 are connected in parallel. One branch is R1, R2 are connected in parallel. Then another branch Vs connected via Rs. Vs is connected via Rs. Okay, it's over. Now base node, we consider all the biasing elements. Let us go and stand at the collector node. What we can see, with respect to collector node, Rc and RL are connected in parallel. Rc parallel to RL. Then we are going to measure the output voltage across Rc parallel to RL. Okay, let us go and stand at emitter node. What we can see, Re bypassed by a wire. There is a short circuit. Short parallel with passive element will be treated as a short. Short parallel with passive element will be treated as a short. Short parallel with active element will not be treated as a short. So now it is a short. So what next step? We have to group all these ground terminals together. I am going to group all the ground terminals together. Rs, R1 parallel to R2, R pi, GM V pi, R naught, Rc parallel to RL. Here V naught. Here it is V pi. Okay. Now this is a small signal equivalent circuit diagram. So again, this is a small signal equivalent circuit diagram. So here this dotted line shows the small signal model of a device. Okay. Then these are the biasing elements. Right. Now let us group the resistances and make the circuit diagram is a reduced form. I can say RL effective. RL effective is the parallel combination of R naught parallel to RC, parallel to RL. Similarly, RB. What is RB? R1 parallel to R2, parallel to R5. Let us draw the small signal equivalent circuit diagram. Vs, Rs, RB, V pi, GM V pi, RL effective. RL effective and V naught. Okay. Now we want to measure the voltage gain. What is the voltage gain? We know the formula. Voltage gain is a ratio of V naught by Vs. So what is V naught? The drop across the RL effective. RL effective, the current flows through RL effective is nothing but a GMV pi. GMV pi is the dependent current source. Okay, when the current flows from bottom to top, it makes the drop like this. But actually reference direction is top positive with respect to bottom. Actual direction of current flow is bottom positive with respect to top. So what is V naught? V naught we can write current GMV pi into RL effective. Okay, since the current flows in opposite direction to the assumed direction or reference drop, we can put minus sign. So V naught by V pi equal to minus GM RL effective. Okay, now we want to know V pi by Vs. So the ultimate our objective is to find the transfer function of V naught by Vs. Now we got V naught by V pi. If you know V pi by Vs, it is possible to compute V naught by Vs. Okay, so what is V pi by Vs? Just like let us apply the voltage divider rule. As per voltage divider rule, V pi equal to, let us assume Is is the current flows or current supplied by the voltage source Vs. Is into Rb. What is Is? Is we can say Vs divided by, there is a input source that is limited by two resistances, Rs plus Rb. The current flow is limited by two resistances, Rs plus Rb. Let us substitute Is value here. Hence it becomes Vs by Rs plus Rb into Rb. That is equal to V pi. Then what is V pi by Vs? V pi by Vs equal to Rb by Rs plus Rb. Let's check, this is equation number 1, this is equation number 2. We know that voltage gain AV is the ratio of V naught by Vs, which is nothing but V naught by V pi into V pi by Vs. So it is equal to V naught by V pi is, using equation number 1 is GMRL effective. V pi by Vs is Rb by Rs plus Rb. Okay, so this is a voltage gain. Then what is the magnitude of voltage gain? Magnitude of voltage gain is GMRL effective Rb by Rs plus Rb. Right? Now let us do some analysis, simple analysis. Assume there is no load resistance. That means RL tends to infinity. There is no load resistance. There is no load resistance. RL tends to infinity. Then what is the change in the gain? AV equal to GM. RL effective is R0 parallel to RC parallel to RL. There is no RL. Hence it will become R0 parallel to RC into RB, Rs plus Rb. Next case. Assume no source resistance, RL tends to infinity. No load resistance, RL tends to infinity, and no source resistance, Rs tends to 0. This is RS, source resistance. So normally practical voltage source will have the smaller value of source resistance, few hundred ohms of source resistance. Now let us assume that it is an ideal source, there is no source resistance, RS tends to 0 and there is no load resistance, RL tends to infinity. Then what is the change in the voltage gain? AV equal to GM R0 parallel to RC. This is the overall gain of the common emitter amplifier, where there is no load resistance, there is no source resistance. So next, let us calculate the current gain A. So we know that current gain A is the ratio of I0 by IS. I0 is the current flows through the load circuit. IS is the current supplied by the voltage source. Okay. So what is I0? Let us apply the current division rule at node A. Apply current division rule at node A. So apply current division rule at node A. So total current is GMV pi. So I0 equal to GMV pi. So for this branch RL, the opposite branch is R0 parallel to RC. R0 parallel to RC divided by total resistance. R0 parallel to RC plus RL. So what is I0 by, see again once again the current flows through bottom to top, what we assume actually top to bottom. Hence the current in a reverse direction when we compare to the assumed direction or referred direction. Hence I0 by V pi equal to minus GM R0 parallel to RC divided by R0 parallel to RC plus RL. Now we want to know V pi by IS. Already we know that the relation. What is V pi? IS into RB. V pi equal to IS into RB. Let us say this is equation number 3. So we can say here 1 multiplied by 2. Okay. V pi by IS equal to RB. Equation number 4. Right. Then what is the current gain? Current gain A is the ratio of I0 by IS. I0 by V pi into V pi by IS. That means equation number 3 multiplied by equation number 4. So current gain AI equal to minus GM R0 parallel to RC, R0 parallel to RC plus RL into RB. Okay. So what next? We found voltage gain, we found current gain. So next one is we have to calculate the transconductance gain and transresistance gain. How to calculate the transconductance gain? GM is the transconductance gain. How to calculate the transconductance gain GM? GM is the ratio of I0 by Vs. Okay. From equation 3, we got the relationship between I0 by V pi. I0 by V pi equal to minus GM R0 parallel to RC to R0 parallel to RC plus RL. Then what next one? This we can write it as I0 by V pi into V pi by Vs. Here let us see. Equation 2 shows the relation between V pi by Vs. So what is the equation 2? V pi by Vs. V pi by Vs is RB by RS plus RB. So what is the transconductance gain GM? GM is the ratio of I0 into V pi and V pi by Vs. So we can say equation number 3 multiplied by equation number 2. Equation number 3 multiplied by equation number 2. So it becomes minus gm R0 parallel to RC divided by R0 parallel to RC plus RL into V pi by Vs is RB by RS plus RB. Okay. So what next? We have to calculate the trans resistance gain Rm. Rm is the ratio of V0 by Is. This can be written as V0 by V pi by Is. Already we know that V0 by V pi from equation number 1, V pi by Is by equation number 4. So I can write it is a product of equation number 1 into equation number 4. What is equation number 1? Minus gm RL effective. What is equation number 4? Equation number 4 is RB. So the small signal, by using the small signal analysis, we have computed voltage gain, current gain, transconductance gain and trans resistance gain. Thank you. So next class we will discuss about how to measure the small signal input impedance and output impedance. Thank you.